All right, so I'm going to look at this exercise 923 just to show you and give you some idea about how much you need to write and what the expectations are. So let's look at A. Why is C star not a group under the operation of complex addition? So just to suggest what you can write here, you can just say, for instance, that 1 and minus 1 are in C star. But 1 plus minus 1 is equal to 0, which is not an element of C star. So C star is not closed under addition. That's all you need to write. Now, you could start out by saying C star is not closed under addition because such and such and such, or C star is not closed under addition, example, such and such and such. That's really all you need to do for A. All right, now, for B, this is the long part of this exercise. You need to show 4 things, so I'll just write them down one by one. And you should use properties from the complex numbers chapter, and you can just cite the property or the exercise without reproving it. So for instance, first we have closure. All right, now, closure means that the operation is closed. In this case, closure means that the product of 2 complex numbers must be a complex number. So let's go back to the definition of product of complex numbers, which is right here. So you could just say something, you could quote this, or you could say, well, I'll just write it down. I'll just say A plus BI times A plus B plus CI is equal to, you could just say, what is it, I'm sorry, not B plus CI, it's going to be C plus DI. It's equal to, what is it, AC minus BD plus, and then the next part is going to be BC plus AD. So the product of complex numbers is always a complex number. All right. Now that's fine. That's all you need to write. All right. So let's do the second one is associative. And here you can just go ahead and cite the exercise that mentions that complex numbers is associative. Let's see, this one says commutative. Let's go down here. Okay, so exercise 2.2.4. So you can say, by exercise 2.2.4, complex numbers are associative. All right, then the next one you're going to do, so don't worry over much if I actually assigned this problem. I think I did, but don't worry about it. You can just assume all of the results in the complex numbers chapter. That's part of math, is building on what you've done already. The next part is identity. Okay. So you can say for any complex number, and let's call it Z, 1Z equals Z1 equals Z. All right, so that's fine. Then you have inverse. And here I think you can go again to the chapter and find the place where it mentions about inverse. All right, I'll give you this one and we can see how you do it. If you want to do inverse, let's go to here. Okay. All right, just say by exercise 2.2.7. Let's see, say every non-zero complex number has a multiplicative inverse. Okay, so that's really all you need to do for B. Just mention all the properties: closure, associative, identity inverse, and just give a brief justification because we've proven all these properties before. Let's see. Now C, that's a one-word answer. D is also just go to the complex numbers chapter, find the relevant property, exercise or the proposition, and cite that exercise or proposition. All right, so let me do a couple of problems very quickly. Here's 925A. Why is it impossible for a set of numbers S which has more than one element, includes 0, to be a group under multiplication? I suggest that you show two things here. First of all, you show that 0 must be the identity element. In such a case, if you have such a case, a set of numbers, show that 0 must be the identity element. Then show that 0 cannot be the identity element. All right, now one is true no matter whether or not S has more than one element. The second one is true. This is only true. This requires that S is greater than 1. Okay. All right. Now, so you should think about what identity element means. Identity element means that ID times any element is equal to that element. All right. So think about those two conditions and show both of them. That will be sufficient to prove the result. All right, for 928, I think I'm just going to talk through this one. Again, if you want to show something as a group, you just need to go through the four properties. First of all, closure. You can just say that by definition, the AB composed CD is a coordinate pair, so H is closed under circle. If you want to show associative, you can just write down what the associative law is and show that it works. Write down what the associative law would imply and show that it works. The basic idea is that the associative law works for each coordinate in the pair, so it works for the coordinate pair. Identity, you can write that down. Inverse, you can write that down. So that shouldn't be more than half a page. All right, just list the properties one by one, work through them very quickly. Okay, so let me say a little bit about 9 to 12. Here we have definition of the product of groups. And we want to show that the product of groups is in fact a group. So what does this definition say? It defines the element of a product of groups, which is a pair of group elements. The first element in the pair is from the first group. Second element of the pair is from the second group. And it also defines the operation. So you need to show the four things again. You can just say that like this, closure. You can say by def 9 to 10 if G1 H1 and G2 H2 are elements of G cross H, then G1 H1 circle G2 H2. is also an element of G cross H. You can see right here, this is what the definition says. If you have two ordered pairs, then the result is also an ordered pair. So there's your closure. Then you have associative property. Write down what that means. If you take G1 comma H1, just write down what it means. Circle G2 H2, circle G3 H3. Okay. Now what's that equal to? It's equal to G1 G2 H1 H2 circle G3 H3, and that's equal to G1 G2 G3 H1 H2 H3, and that's equal to, now I can use the associative property on the individual groups, so that's equal to G1 G2 G3 H1 H2 H3, and this is by associative property of G and H. Okay. And that's equal to G1 H1 composed G1 G2 G3 H2 H3, and that's equal to G1 H1 composed G2 H2 composed G3 H3. Okay, all right. That's a little bit more writing, but it's still only 4 lines. All right, then identity should be very straightforward. Just exhibit an element such that the product gives you the original result. So you could say something like this: let, if you want some notation, you can say let EG be the identity. Well, let's just say it this way: let IDG and IDH be the identities of G and H. Then, so you need some identity element, and then you say comma composed with GH equals GH composed with whatever element you're going to do is equal to GH. That's enough to show identity. And then you do something similar for inverse. You would say let G inverse and H inverse be the inverses of G and H, and then write down a similar statement to get the inverse. Okay, for exercise 9.2.15a, you just want to see whether these group Cayley tables correspond to groups. And don't waste your time writing down a lot of stuff if it's not a group. If it's not a group, then just go ahead and say it's not a group and tell why, and then move on. For example, for part A here, first of all, you can check if it has identity. Now notice that you can assume the associative property, so you don't need to check that one. Well, and they all have closure, so you're not even going to have to check that. It's clear they all have closure because all of the letters inside the table are letters on the margins. So let's check identity. In this case, identity is A, because A circle X equals X circle A is equal to X for all elements, and you can write it that way. Then you also have to check inverse. So let's see. It's clear that A is the inverse of A because A times A is equal to A. Looks like B is the inverse of B because B times B equals A. So then it looks like C is the inverse of C. Now what about D? Here you have D times B equals A. but you don't have B times D equals A. So you can simply say D has no inverse because D circle B equals A, but B circle D is not equal to A. All right? So in fact, you could just write that single statement and move on. Or actually, you would need to mention that A is the identity. So you could say for part A that element A is the identity because A circle X equals X for every X in G, but D has no inverse because D circle B equals A, but B circle D is not equal to A. Okay, so you can just give the statement and the reason. Shouldn't take too much writing. All right, for 9.2.16, you don't have to give reasons for filling in the blanks. You don't need to write down the reasons, that is, but of course you should have a reason. Okay. For instance, you can pretty much tell what this element's going to be. You don't need to give a reason, just put it in and then make the whole table work. Just make sure you've got your identity and inverse. You can assume associativity. Okay, that's it for the problems that I'm going to review in 9.2. Make another video for 9.3.